Institute for Energy Efficiency, and this seminar is coming to you from Henley Hall. Galan is sitting in his office there in the third floor. So as you can tell from my picture, I'm sitting on the curb out front. So hi, Galan. Yeah, we're delighted to have Galan speak today. I think, as everyone knows, he came here about 3 years ago from NIST, where he was a research scientist working in Rich Mirren's group, and he's just had a great impact on UCSB already, working in all kinds of quantum projects and contracts in the quantum foundry, and really just been a leader for us. So we're delighted to have him speak. I'll turn the floor over. I don't know if you want to wait with questions till the end, or do you want to entertain them along the way, Galan?
Either way is fine. If anyone has questions, you can just chime in, and I'm happy to answer them going along, or at the end.
Okay. So otherwise, maybe keep your microphone muted, but yeah, go ahead and unmute it and ask questions. So without further ado, Galan Moody is going to talk about quantum computing with light. The floor is yours.
All right, great. Thanks for the introduction, John. So today I'd like to give really just kind of like a high level picture of some of the projects that we're working on using integrated photonics for quantum computing. And I'm sure everyone's very aware of like the recent Google results from 2019 demonstrating a quantum advantage using superconducting circuits. So to kind of put where we're at with integrated photonics into better context, let's kind of start with just an overview of where the field of quantum computing is at right now. So there's a number of different ways how we can kind of present this. One way is to just present the number of physical qubits for quantum computing across different platforms. So in this figure, I'm going to show, for example, the number of qubits on a log scale versus sort of a timeline here. And so we have first, for example, one of the technologies is superconducting circuits. And this, of course, is been being commercialized and developed by Google and a number of other companies. So you can see a nice steady progression of 2 qubits in sort of the 1990s, progressing all the way up to an expected more than 100 qubits coming out this year. And of course, this technology has been adopted by a number of companies, including Google, IBM, Intel, Rigetti, and a number of others that I'm not listing. This is not an exhaustive list. So quite impressive results coming out of this platform. There's another company called D-Wave who are also using superconducting circuits sort of in a different architecture that's called quantum annealing. It's probably a little bit less general than the gate-based quantum computing model that these companies are using, but nonetheless, really exciting results coming out of D-Wave and impressive scaling, for example, up to thousands of qubits for their system. Another technology is based on trapped ion technology, and you can see here a very nice image of sort of tens of ions trapped on this chip. Upwards of, I think, expected about 32 qubits coming out this year. And this is also being adopted by a number of companies that are really pushing the field forward, for example, IonQ and Honeywell. And I would say a little bit late to the game is optics and integrated photonics with some nice results that are sort of coming out in these past few years. And so really sort of like a 2 qubit demonstration with integrated photonics in 2018. And this year, for example, 8 qubits demonstrated on chip for quantum computing. Of course, this technology is now being developed also and pushed pretty heavily with a couple of startups, Xanadu in Canada and PsiQuantum in Palo Alto. And so some of these platforms are capable of demonstrating a quantum advantage. And so Google came out with their results in their superconducting devices in 2019. And China came out with some results demonstrating a quantum advantage in 2020 with bulk free space tabletop optics, basically filling the lab. A really cool, impressive picture here showing their system. So just a very quick overview and rundown of what they're actually doing with these devices. They can take their quantum system and run some sort of quantum circuit on their device. They can then measure the bit strings that are coming out. And then they try to also do a classical computation to predict what they would get. And then they kind of compare how expensive is that computation. If it's too expensive, then you've reached this sort of regime of a quantum advantage for this particular circuit. So these are really impressive results demonstrating a quantum advantage for one very specific quantum computation, not really a general purpose useful quantum computer yet, though we're still quite a ways away from that. And the main challenge is that qubits are still too noisy. And at least for optics, and for this example in particular, the optics is too lossy, and bulk tabletop optics isn't really scalable. It's not a scalable approach. So you really need integrated photonics to be able to scale that up even further. So we're really at the level of tens of sort of noisy qubits versus sort of a million that we probably need to have a really general purpose useful quantum computer. So we're still quite a ways away from achieving that. So what's needed to build a genuinely useful quantum computer? I think there's sort of three main components for the technology that you're developing. The first one is you need a technology that can be reliably manufactured. So you want to be able to scale that up, and you don't want to have fabrication imperfections that sort of make a lot of the devices not work properly. You want your approach to be fault tolerant with error correction. And then you need some practical path to scaling to 1,000,000 qubits. And so if you're not satisfying these, at least in principle, then you may face challenges with the given platform that you're using to scale up to the number that's needed. So I think this is really where the advantages of light come in for quantum computing. And so there's sort of four main advantages that I can see. First is the low noise optical systems. We can make really nice single photon detectors, really quiet light sources, and that results in efficiency and reliability of the systems. You can also leverage the well-established techniques and wafer scale fabrication methods that have really been developed for the past couple of decades for integrated photonics for classical communications and high-speed interconnects and things like that. And of course, to scale up to something like 1,000,000 qubits, you're not going to do that on just a single wafer or single chip. You really need to have a lot of interconnected devices. And this, I think, is one big advantage of optics and integrated photonics in particular, is that it's a perfect platform for quantum computing and communications in the same physical architecture. And so then you can envision making networked quantum computers sort of naturally with this platform. And in terms of the qubits themselves, we're going to encode information in photons, and we can create chip scale sources that generate millions or billions of entangled photons per second. So what this means is that we can have really high clock rates in our devices. And so, as John mentioned, I came to UCSB a couple of years ago in fall of 2019, and I run the Quantum Photonics Lab, which is in Henley Hall. We just sort of opened up our lab. It's a little bit of an old picture, but here's a picture of our lab where we're starting to build up some of the experimental capabilities in my group. And so we work in three sort of complementary areas. The first one is in turnkey quantum light sources. So we're just trying to develop much better quantum light sources that produce higher quality states at higher rates with higher efficiency and lower optical powers that are needed to pump the sources. We also work on quantum frequency conversion, so converting photons to different wavelengths that we need for certain applications, and then making large-scale integrated quantum photonic circuits. So we have all-on-chip functionality for applications in computing and communications. Okay, so in this talk, I'd like to give a really nice sort of high-level overview of some of the stuff that we're doing in our group and at UCSB as well. And so I'm going to talk about optical qubits and just give an introduction to what I mean by optical qubits, as well as ways for photonic integration. And then I'll talk about one specific programmable photonic architecture, one approach to computing with light. There's many different ways you can do it. We're pursuing a few different ways. I'll talk about one of those. And then I'll talk about the silicon photonics dilemma and what I mean by that, probably in the last third of my talk. Okay, so let's start at the very beginning, at the basics. A classical bit versus a qubit. So classical bit, semiconductor transistor, it can have an off state or an on state, 0 or 1. The key difference between a classical bit and a qubit is a qubit can be 0, 1, or any superposition of 0 and 1. So it can be in this coherent superposition of these two states. And so that's the key fundamental difference between a qubit and a classical bit. So as an example, let's say we have 3 bits versus 3 qubits. For classical bits, 0 and 1. So if we have 3 of them, for example, it could be 1, 1, and 0. And so what this means is 3 classical bits gives us 3 bits of information. That's pretty intuitive and pretty obvious. For quantum systems, for qubits, it can be 0 or 1 or some superposition of the two. So if we have 3 qubits, then we have 8 possible states. We have 8 bits of information. And this is where the real advantage of quantum bits or qubits come into play, is that for in qubits, you have 2 to the n bits of information. So you have this exponential scaling, and that's the real advantage of quantum computing. So how do we encode qubits into photons? It's important to realize that the photon itself is not a qubit, but there are many ways to encode a qubit using a photon. So let me just kind of walk you through what a few of these different ways are that you can use the degrees of freedom of photons to encode information. The first one is called a path qubit. So it's pretty simple and straightforward. It's if you have a single photon and it's traveling along one path, like a top path here versus the bottom path here, you can define which path the photon is in as the qubit itself. So you can define this path is 0 and this path is 1. And then you can try to put the photon or manipulate the photon into some superposition of these paths to then write some general state for your qubit. Another way to encode information of photon is to use the polarization. So the orientation of the electric field of the photon can be used to encode information. So whether the electric field is oscillating in the horizontal plane or the vertical plane, you can use that to define your qubit of your photon. There's other ways to encode information. For example, in time bins, is your photon in some early time bin that you've defined, or is it in a later time bin or some superposition of the two? And also frequency bins. So did you generate a photon and produce that photon that has some frequency omega 1 or some other frequency omega 2 or some superposition of the two? And so a number of groups worldwide are basically using these different degrees of freedom for different applications. As an example, the polarization qubits and time bin qubits are often used for quantum communications. For chip scale quantum computing, frequency bin qubits and path encoded qubits are more commonly used. And it'll be a little bit clear why path encoded qubits may be really useful. So I'm going to focus on these path qubits and discuss how we can use these qubits for information processing. And this is otherwise known as dual rail encoding because you've got these two possibilities for where the photon can propagate. So if we have a single optical qubit or just a single qubit in general, we need to be able to perform single qubit operations. We need to be able to control the quantum state really precisely. And so to do that with photons, it's actually pretty straightforward how to do it with bulk tabletop optics. And as an example, we could take what's called a Mach-Zehnder interferometer. So this is just a 50-50 beam splitter. This transmits or reflects half the light. This is another 50-50 beam splitter and then two mirrors. And you can make this interferometer such that light that's coming in can then travel along two paths, and then you get interference at the output. And so we can define a photon traveling along the horizontal direction as 0. So that path is the horizontal path at 0. A photon traveling along the vertical direction here, we'll define that as our qubit state 1. And then we can arbitrarily adjust the phase of this path and the phase of this path, and then also the relative phase between these two arms by slightly moving this mirror to perform certain operations on these photons. So we can do this then to generate any arbitrary quantum state of the photon being in either of these paths at the output of the interferometer. And so we've done exactly this actually in a teaching lab that I've been working on and teaching in my class this past quarter. One of my students, Quinn, has helped me set up this teaching lab. And so here's just a picture of what this looks like in the teaching lab. Here's a top-down view. Here's the first beam splitter, the second beam splitter, and then here are the two mirrors. And so kind of traced out here sort of the paths that the photon could take. So what we do in this experiment is we have a single photon source. Students will send single photons into this interferometer. The photons can propagate along either of these paths and then interfere at the output here. And then we have a single photon detector at the output to then measure what is the probability that the photon is in this path versus the upper path here. And then we can control that probability amplitude by adjusting the position of this mirror with really precise delay stage to introduce a very precise phase to then look at interference at the output here. So if we actually measured basically what is the count rate, how many photons do we get per second at the output here, we can then relate that back to what is the probability of the photon being at this output as a function of this phase. And if you do that measurement, then you can see that you get very nice oscillations with probability between 0 and 1. So students can work through this lab and understand single qubit operations and how to control that. And so we can do this with free space tabletop optics, but you can see that this isn't necessarily a great scalable approach. Each one of these holes is spaced by 1 inch. So this is a fairly large apparatus. So imagine trying to scale this up. It gets pretty unwieldy pretty quickly. So we can use integrated photonics to solve that problem. And so here's a chip scale sort of illustration of an integrated photonic Mach-Zehnder interferometer. So here's the first beam splitter. Here's the second beam splitter. And what I'm showing here is basically waveguides. So you have some high index material surrounded by some low index material. If you couple light into one of these waveguides, then it'll couple nicely to this optical mode. So if you send a single photon, for example, into this waveguide, we're going to define that as our qubit state 0. And then if it's in this waveguide, we'll define that as our qubit state 1. So this is the path encoding that naturally comes just from integrated photonics. And so by adjusting sort of the current through these different heating elements, we can adjust the phase of the photons and basically create any arbitrary state of the photon in these two paths. So that allows us to give us very nice control over the qubit state. And so this is a highly manufacturable technology. You can make thousands of components per chip with really high reliability. You can perform really high fidelity operations. So we can perform arbitrary single qubit gates. And I'll talk about how we can do entangling operations between separate qubits. And then this is fairly loss tolerant. And there's ways to make this loss tolerant. Okay, so how do we go from 1 qubit to an optical quantum computer? That's much more challenging. So we're sort of at a path here that is reminiscent of what digital electronics really went through, and like starting sort of in the 1950s and beyond. You start, with vacuum tubes, and then develop the first classical computer, which then became very scalable with integrated technologies. We're at the same sort of juncture, I think, with all quantum systems, but especially with integrated photonics quantum systems. And so we can easily perform single qubit operations. We can even perform a few qubit entangling operations. And we can demonstrate a quantum advantage. And we're going to see a lot more demonstrations coming this next decade, for example, by different companies and different research groups worldwide. And the question is, at what point do we get to having a useful integrated photonic quantum computer? And that's still an open question, but I think the prospects are really bright for integrated photonics because of the intrinsic scalability of just scaling up the size using integrated photonic technologies. And there's a lot of progress that's been made in this direction in the past decade. And so there's a nice review that John Bowers and I and a couple people in our groups have put together this past year. That kind of shows the timeline from really about a decade ago to this past year in the progress that's being made in this direction, sort of starting with 2 photon interference on chip all the way up to more complex circuits that have upwards of 1,000 components for manipulating quantum states. So let's talk about how to actually perform any sort of computations using photons on a chip. And I think one way to do this is to compare it to the standard circuit-based quantum computing model that I think more people are familiar with like superconducting qubits, for example. And so the circuit-based quantum computing model, what you do is you start out with a number of qubits, and your number of qubits is going to be fixed. And then what you do is you perform a sequence of operations on different qubits. They're either single qubit operations to manipulate the state of each qubit, or they could be entangling operations to entangle different pairs of qubits. And then ultimately you do some sort of measurement on various qubits in your system. So for example, if you have some array of qubits that initially are untangled and they're just prepared in some state, like the ground state, you can implement some sort of entangling operations between those qubits. And then maybe at a later time, you could implement different entangling operations or single qubit operations. And then you can do some measurements at the end. And that's how you can run your computations, keeping the number of qubits constant and static, and just sequentially performing certain operations. So that's one model for quantum computing. Another model is the measurement-based quantum computing model. And so in this case, computations proceed through measurements. And that's different than what I just described, where these computations proceed through gates, through operations on the qubits. Instead, what we do is you can start with a large resource of entangled states. Let's say we have this 2-dimensional array of photonic qubits that are all entangled. Then you can perform operations, single qubit measurements on various qubits within this large array to then drive computations forward. And so if you have your resource here, this resource state where all the qubits are entangled, then you can perform a certain measurement on some subset of the photonic qubits. That destroys the photons. And so you reduce the size of your resource state. But then on the front end, what you can do is you can perform entangling operations to then add in additional qubits. So you can keep the resource size the same as you're continually doing these measurements and replenishing the number of qubits that you have in your photonic system. And so here's one example of what that could look like. If you have sort of an array of entangled qubits to begin with, you can start performing certain operations, certain measurements on some of the qubits. That can then inform you of what you should do for future measurements. And you can use this to basically map any sort of quantum circuit onto this large entangled resource state. And so this circuit here, for example, looks like a three logical qubit circuit. And then you have some entangling operation between these qubits, and then later on an entangling operation between these qubits. And so the challenge with this kind of measurement-based computing model is to create this large entangled resource state to begin with. Once you do that, then all of these operations are actually pretty straightforward. They're very simple single qubit operations that you can do with integrated photonics very, very easily. So how do we create these resource states to begin with? Like I said, that's the key challenge for photonic computing. So there's one somewhat simple way to do it. And it's called Bell state generation. Let's say we had 4 individual photons and they went into, I'm showing this as a black box right now. What you could do then is you could measure 2 of the photons. And if you get a click on this detector and a click on this detector, that'll entangle these 2 other photons. So you get rid of 2 of the photons. You lose 2 of them through a measurement, but that entangles the other 2 that are remaining. So that's one way to at least create a 2 qubit entangled state with photons. You can scale that up to an extent. As an example, if you had 6 photons, you could send it in some other black box, do a measurement on 3 of them, and that'll give you 3 entangled photons at the output. And so you could do this with like tabletop free space optics with some pretty simple linear optical components like beam splitters and single photon sources and detectors. Everything that we have technology to be able to do this today. So then the challenge is, okay, so we could do this and create 2 entangled photons or 3 entangled photons, but it starts to get kind of unwieldy if we try to scale that up. So another way, instead of just trying to make these boxes bigger, is to take some subset, some separate resources, and then try to entangle them together to make larger resource states. So as an example, if we had some source that could produce 3 entangled photons and a different source that was also producing 3 entangled photons, we could actually just send these into a very simple integrated photonic beam splitter with detectors at the output. If you do a measurement on these 2 photons, it'll destroy those photons, but that'll give rise to an entangled state of 4 photons at the output. So you've used up a couple of the photons, but overall you've increased the size of your resource state. And this requires pretty simple hardware that can be fabricated with high reliability and pretty high volume using integrated photonics. The challenge is that this is a probabilistic measurement. So this is not deterministic. You're not going to create this state every single time. It's a probabilistic process. And so how do you get around that? There's one way that you could potentially get around it, and you could do something like multiplexing. So you could take an array of these entangling operators, and then whichever one is successful, you just switch that in to the rest of your network. So you can switch out the unsuccessful operations to then deterministically generate your resource state. So you could make large scale arrays of these things and then make fairly fast switches on the order of maybe a nanosecond and allow you to then make these resource states. What's nice about this approach is the hardware overhead is constant. And that really means that larger computation means making more states, not bigger states. And so you can use temporal multiplexing and fiber delay lines to then extend your computational depth while keeping the overhead the same. And so you don't have this overhead issue that other quantum platforms might have. So here's an example, like an illustrative example of what a photonic chip may look like to create one of these types of resource states. And this is something that we're pursuing in our group to build up in our platforms. So I won't go into specific detail of this, but just to give you a high level overview of what we're trying to do. We start with entangled photon pair sources, and we're going to pump these sources with a laser that's off chip that will couple light on chip using fiber. Then we can have very simple interferometers on the chip to separate out the photonic states, and this gives us our qubits. And then we can perform certain operations on a subset of those qubits using simple linear interferometers. And then we can do operations or measurements using, again, simple linear interferometers. And then at the output, we can detect the photons using single photon detectors to verify that we've made the states that we've really wanted to make. And so this allows us, for example, this architecture would allow us to make a 4 qubit graph state. And that what that really means is we have 4 qubits and they're all entangled with each other. And so then the challenge is, how do we scale that up? And so one way to scale that up is to make arrays of these resource states which is actually fairly straightforward. If you can make one of these, then it's fairly straightforward to scale that up on chip. And so these are going to be producing these graph states probabilistically. So what you can do then is you can couple that light into an integrated photonic chip that allows you to switch which one was successful. And then using a fiber, you can couple that light out and make this sequence of graph states and basically build up a network this way. And so the fiber effectively acts as a memory. And it's sort of a propagating memory. You're not storing it in some static state. You can kind of sync everything up to a clock and basically build up your resource states this way. And this is why you have a constant overhead in your system, because you can use this sort of temporal multiplexing. And there's a lot more details on exactly how to do this in a really nice review article that came out recently from PsyQuantum. Okay, so there's some nice demonstrations of these sort of approaches to quantum computing by sort of the two leading companies, PsyQuantum in Palo Alto and Xanadu in Canada. They basically use these same concepts, but they use effectively different resource states to begin with. And so PsyQuantum uses what's called discrete variable or individual photons. That's basically what I've been talking about. You have some sort of resource that generates individual photons that are entangled with each other. They are leveraging a foundry manufacturing processes. So they've partnered with global foundries using silicon-based photonics. And that means that they have a very nice, scalable, and reliable technology. They can perform basically near perfect single qubit measurements. The challenge is that their sources are probabilistic, and the entanglement generation between the different resource states is also probabilistic. So they have to develop these switching and multiplexing components to be able to try to make that deterministic, to even make that scalable. Nonetheless, a related group to them in Bristol in the UK, they've demonstrated up to 8 qubits with this sort of approach. The challenge is that it's been pretty slow in terms of the processing speed and it's sort of millihertz clock rates. So Xanadu is using a very similar idea, but they're using continuous variables to encode their qubits. And so this is basically squeezed light. Instead of entangled photon pairs, they're using squeezed light. And I'm not going to go into the details of the squeezed light sources. I'll just kind of give an overview of what they're doing and a little bit of the differences. So this relies on the generation of squeezed light on chip. One advantage of doing this is that you can have deterministic state production. So you can produce these squeezed light sources deterministically, and that's to contrast with this approach, which right now is probabilistic. So up to 8 qubits have been reported with their approach. They also use a foundry manufacturing process that's based on silicon photonics. The challenge is they have limited squeezing using silicon-based photonics. And so this kind of opens up a question of, is silicon-based photonics the optimal choice for quantum photonics? It's manufacturable and it's scalable, but is it really the right material platform? The reason I ask that is it's very low loss, but the photons that are generated on chip are all generated with nonlinear optics. It's a nonlinear process to create these photons. And so these nonlinear processes take some sort of laser light that's coupled on the chip, and then it's converting those laser photons into 2 new photons at different frequencies. And that's a nonlinear process. So to make that as efficient as possible, you want to have a highly nonlinear material. You want to have very low loss, and then you want to have a really high optical confinement in order to increase the intensity, which then improves the efficiency of your nonlinear process. Okay, so I'm not going to go into this table in any detail. I just kind of want to show a comparison of different photonic materials, because this can inform us on what material might be the best to use for these nonlinear processes to try to make the photonic state generation as efficient as possible, which means it is as quick as possible, as high of a rate as we can achieve. So there's a number of different materials that have been developed for integrated photonics for various applications. Here are just a few different key properties that we care about for these different materials. So the Chi2 and Chi3, these are the optical nonlinearities. The quality factor, this is basically inversely proportional to the loss of your photonic system. So the higher value here, the better. The refractive index can tell you about how tightly your optical mode is going to be confined in the waveguide, which then increases the intensity of your optical beam in that waveguide. The band gap tells you about any issues with absorption. And then this column kind of shows you if there's prospects for integration with active devices. So I really just want to highlight these 3 materials here. So silicon and silicon nitride are the most widely used, and I think it's primarily because of this foundry manufacturing process. You can design your chips, send those designs out, you get your chips back, and then you can do all your testing. And you know that what you get back is going to be designed and fabricated properly with high reliability and high yield. Um, in my group, in collaboration with John Bowers, we work with 3,5 materials, primarily gas and algas. And so just to compare this material to silicon and silicon nitride, it has a higher Chi3 nonlinearity and it has a Chi2 nonlinearity. These two materials don't. It has a pretty good quality factor, which means that the waveguide loss is fairly low, has a fairly high refractive index, and it has a wider band gap than silicon. And that's going to be important at telecommunication wavelengths to reduce the loss due to two-photon absorption. And so just based on these properties here on their own, one would say that algas is probably a better material for integrated quantum photonics, for quantum light generation. It's fairly low loss, and the higher nonlinearities is going to help with generating these quantum states of light. So there's been some progress at UCSB and in collaboration with NIST in nonlinear photonics with 3,5 materials, and so I'll just highlight a few of those here. Sort of wafer scale development of aluminum gallium arsenide that's been bonded to silicon. And these devices have been designed for multifunctional integrated photonics in the mid infrared with pretty low loss spanning up to almost 5 microns. There's also been devices that we've worked on for record high second harmonic generation efficiency on chip, basically converting photons at 2 micron down to 1 micron. And then also in the Bowers group, they developed the algas on insulator platform for ultra low threshold quantum frequency comb generation with very low pump threshold powers, down towards sort of tens of microwatts for the comb generation. So very nice results in the past couple of years coming out. And so this past year, we've also worked with this platform, the algas on insulator platform, to use that to generate entangled photon pairs. And that's kind of what I want to talk about in the sort of last third of this talk. So here's an example of what one of these devices look like. It's this micro ring resonator coupled to this waveguide bus. And so we can couple laser light on chip, and some of that laser light is going to couple into this micro ring resonator. And then those photons are going to get converted into entangled photon pairs that we're going to couple off chip and do measurements on to characterize the system. And here's sort of a zoom in image of what one of these chips look like with an array of these sources on the chip. And then we basically take some fiber, couple light on, and fiber to couple light off. So here's kind of what the optical mode looks like in this system. It's an algas. It's algas basically sandwiched with an oxide cladding, and so we get very nice tight modal confinement because of the large index mismatch. And one nice advance of this material platform is in the fabrication process, we can create these devices with very nice smooth features here. And that's really important for reducing any scatter of the light off of that algas oxide interface. And that then allows us to improve the resonator quality factors and reduce the waveguide loss in these materials. And so here's a really conceptual figure of what's actually happening in the device and how we can create these entangled pairs. If we couple laser light into this waveguide, that light can couple into this resonator and circulate around. And then what happens is through a nonlinear process, 2 of these laser pump photons will get annihilated, and they'll generate 2 new photons using conservation of energy and conservation of momentum, but these will have different frequencies, and they'll have certain properties that are correlated, and I'll show that they're highly entangled states. So if you look at a transmission spectrum of this device or of this device here, so basically you can pump your laser light into this waveguide and then just look at the transmission of the laser light coming out. As you sweep the frequency of the laser, you'll see that you have these very nice dips here, and these correspond to the different modes of your resonator. So what we can do is we can lock our laser onto this resonance here. So we just park our laser here, and then that will then generate 2 new photons as we annihilate 2 pump photons at these additional sideband frequencies here. So we're going to detect photons at these wavelengths as we are pumping at this wavelength. And what's important about these devices is we're going to look for entanglement across these 2 photons, these new photons that we're generating. And that entangled pair generation rate scales as the nonlinearity squared of your material, the quality factor cubed of your device, and then 1 over the radius squared. So you want as small of a radius as you can without diminishing your quality factor. And then you want a material as high of a nonlinearity as possible. So here's what the experimental setup looks like. I won't go into the detail of this, but we basically take our tunable laser, we couple that laser onto the chip, and we center that on the wavelength that we care about for pumping that one optical mode. We couple light off the chip, and we send it through various components like an interferometer and some filters and different things like that. And ultimately what we do is we detect photons on really high efficiency single photon detectors. So here's kind of what the chip looks like. We stabilize its temperature. We have a fiber coming in and a fiber coming out. Here is what the detectors look like. They're fiber coupled superconducting nanowire single photon detectors. They're provided by a company down in LA, Photon Spot. They make amazing devices, really high efficiency, really low dark counts. So these are really high quality detectors that allow us to do these kinds of measurements. And then what we do is we record every time a photon hits one of these detectors. This one's detecting the signal photons at one of those wavelengths. This one's detecting the idler photons at the other wavelength. And then we're just basically recording those as a function of time. So we're time stamping every time we get a photon. Okay, so here's a little cartoon of kind of like what's actually happening in our device and how we're going to verify if we have entanglement in these photons. If we think of our chip as some sort of nonlinear material, I'm just showing it as a box here, then what we're doing is we're taking a continuous wave pump laser and pumping this material. That laser does have some coherence time, some line width associated with that frequency. So the coherence time is like on the order of 100 microseconds. And then what we do is we turn the power down in that laser enough such that the probability to generate multiple photon pairs in a given time is very low. So what we want to do is we want to convert two of these pump photons into two new photons, but we want to keep that so that we only create one of those pairs at a given time. And so if we then look at the output, what's coming out, here's sort of the envelope of what the laser looks like. And each one of these envelopes here is a photon pair. And that can happen anywhere in this distribution of this laser here. So this process is probabilistic, and so we can get a photon pair out anytime within this 100 microseconds. And so what this produces is a highly entangled state across this continuous distribution of the laser within its coherence time. And so to verify if we have entanglement, what we can do is we can compare photons at one time to photons at another time. We can interfere them in one of these Mach-Zehnder interferometers and see if we can see interference between these photons and these photons. So as an example, if these photons are separated by 40 nanoseconds, we can create an interferometer that has a delay line of 40 nanoseconds to basically sync these photons up in time with these photons. So that's kind of what this interferometer here looks like. If we couple both of those photons into this interferometer, we can split them out. Here's one arm of the interferometer. We have another arm of the interferometer with some additional delay. This is a fiber delay line. That then basically syncs up those two photon pairs on top of each other. And if they are indeed entangled, then we should see interference at the output here. And so what we can do is sweep the phase of one of these arms and then look for interference. We'll get destructive interference and constructive interference as we sweep that phase. And so indeed, that's exactly what we see here. And so this central peak kind of shows that as we adjust the phase of this interferometer, this peak goes away. And that's sort of the hallmark of this type of entanglement from these sources. And so the data looks quite nice. If you look at sort of the counts on these detectors, you can see that as we sweep that phase, we get very nice destructive interference, and then ultimately we could get really nice constructive interference. So we get what's called a visibility, which is basically the max minus the min over the sum. That visibility is above 97%. So we have very nice entangled photon pair states coming out of this device. And what's, I would say, more exciting about these results is if we look at the entangled pair brightness. This is basically the number of pairs that we're producing per second versus on this axis, the nonlinearity of the material. And I'm showing different materials here, for example, aluminum nitride, lithium niobate, silicon nitride, silicon on insulator, and indium phosphide. And of course, all the way up here, which is what's really exciting, is the AlGas on insulator platforms. We basically have a 1,000-fold improvement in the brightness of our entangled photon pair sources compared to silicon on insulator, which is more commonly used. And so that's, I guess, maybe not super surprising. We have really high nonlinearity, we have small ring radius, but the big challenge was to make sure that the loss remains low in this platform. And that's where a lot of the development has gone in the past couple of years to enable these results. So here's a table that summarizes all the different parameters that we've characterized for the source, comparing it to all these other approaches. And so some of the key takeaways from this is that the AlGas insulator platform is really low loss comparable to silicon insulator and silicon nitride for quantum photonics. It has a large Chi3 nonlinearity, small ring radius, large Q. What this translates to is a pretty good conversion efficiency and about 100 times lower pump power on chip for a given pair generation rate. So we can dramatically reduce the on-chip power in our devices, which is really important if we want to integrate everything on chip, including detectors. We want as few of the pump photons as possible kind of scattering around on the chip. We expect similar performance advantages if we want to use these sources for squeezed light generation. And so that's an interest going forward, is to demonstrate squeezed light on chip using these types of sources. And then there's some very nice prospects for all on chip integration. So this platform is compatible with integrating gain, single photon detectors, modulators, and so forth, other active and passive components for complex functionality on chip. And so we've been working in the past few months on doing some of these sort of things. And as an example, we can make these sort of tunable Mach Zehnder interferometers on this platform. And we can use this either to filter the pump light on the chip quite nicely, or we can actually use it to separate out the qubits into different spatial paths on the chip. And so we have very nice performance in terms of sort of the extinction between different wavelengths. And this performance is quite comparable to silicon. And then I've done some work in collaboration also with NIST in the past few years on integrating superconducting single photon detectors on chip. So here's one image of a bunch of different waveguides and some of these superconducting detectors. And we can achieve a pretty nice performance in terms of nice quantum efficiency, high detection rates, really low dark counts. So nice high performance detectors integrated on these types of materials. So to sort of like summarize all this and put this all together and where we're going for the next year, we're pretty excited about this platform because the sources are really bright and the platform itself is very low loss. And so we can start thinking about adding more on-chip functionality, like I've kind of discussed, to do something like create a chip to generate this 4-qubit graph state. And what we expect is due to the low loss and the high generation rates of our sources, we expect a significant improvement in the computational speed and efficiency compared to silicon photonics. The brighter on-chip quantum light sources that we can develop for sort of discrete variable or entangled photons can then be translated hopefully to continuous variable for squeezed light. And so that's kind of where we're going for the next year. And I'd like to summarize by just acknowledging everyone in my group who's been amazing working on all of the different projects that we have going on in the group the past year, very productive despite everything that's been going on. And especially acknowledge Corey, Josh, Quinn, and Trevor, who've been working on these particular projects that I've been discussing. And we collaborate quite a bit with John Bauer's group and a number of people there. And I'd also like to acknowledge Lynn working on these projects with us. He's been extremely helpful. So we have funding from a number of different agencies. I'd just like to acknowledge all the support's been extremely helpful, especially a seed grant from the Institute of Energy Efficiency. And also a little shout out here that we have some openings for graduate students in photonic quantum computing. So if you're interested in listening, contact me at this email address and we can chat about some of these opportunities. So with that said, thank you all for your attention. I'm happy to stick around and answer any questions.
Great. Thank you, Galen. Very nice, very informative. Questions from people? There's one in the chat from Larry Kelly. What physical constraints are there, e.g. operating temperature?
Yeah, that's a great question. So right now everything is done at room temperature and it can all stay at room temperature unless you want to integrate detectors on the chip. The best single photon detectors are superconducting single photon detectors. And so those need to be cooled down depending on the material to 4 Kelvin. So there's prospects for doing sort of all on chip with detectors at 4 Kelvin. But what we do right now is basically everything on chip except for the detectors and then fiber coupled down to detectors that are cold. So that's one prospect that we are going to push forward, is just developing detectors and arrays of detectors, keep those things cold, try to make better interconnects that are low loss to couple from the chip to the detectors.
Ted's asking about scalability to 1 million qubits. You want to sign up for that next year or year after, Galen?
I think was Ted signing up for that. I mean, that's going to have to happen at like a big company like PsiQuantum. That's not something that we're going to be doing at a university. we just don't, you don't have the resources. I mean, companies like Xanadu and PsiQuantum have hundreds of millions of dollars. And so that's kind of the funding level that's going to be needed to be able to do that. Fundamentally, I think the prospects are actually pretty good. You're going to have to connect a bunch of chips together with fibers. And so you need to have really low loss interconnects. But otherwise, at least with their platform, with wafer scale silicon photonics, there's no issue in terms of scaling with that aspect. For our
the comment is, I mean, you said 1 million, but it would seem to me with 10,000 qubits, you could actually make a
yeah. So the idea of the million is that you need redundancy and error correction. So if you had perfect qubits, you wouldn't need that many. So that number is sort of the accepted number based on what we may expect based on errors of different quantum platforms. You could certainly do something in the sort of tens of thousands, especially if they're not too noisy. And so with integrated photonics, and especially with the AlGaAs platform, we're focused more on demonstrating the advantages of that platform compared to silicon, with the hope to say that, okay, this is a much better platform. It may not have the manufacturability yet of silicon photonics, but if we can demonstrate the performance, then I think there'll be a lot of interest and a lot of investment to then understand how to scale this platform up further.
Other questions? Feel free to unmute yourself and ask it. Maybe I'll just take the liberty now. If you go back to that slide comparing generation rates, comparing different materials.
Yeah.
Yeah, I'm surprised by indium phosphide being that bad. It's what, over 1,000 times worse.
Yeah, I think
it
should be better.
1,000.
Yeah, it should be better.
Yeah. So that's experimental. That's not calculated. Is that what you're saying?
Yep, that's experimental measured. I think that if you can make better indium phosphide microring resonators, then in principle it's going to be pretty close to as good as our platform.
Okay, so if you had a theoretical plot, it would look very different from this then. Yeah,
I think it would. Yeah. And it's important to note that you can make really high quality resonators in silicon or silicon nitride much better than what groups have used for this data. The challenge is to make those such that you can get really high generation rates. And so you could make a millimeter ring diameter and get really high quality factor for your resonator, but you're going to end up losing out on your pair generation rate because your ring is so big. So there's this trade-off and this balance to find the right sort of geometry for your system to try to optimize your entangled pair brightness. And that's one advantage that the AlGaAs platform has, is that for the ring radius that we've used, the quality factor is actually higher than some of these other platforms. So,
other questions? All right. Let's thank Galan. It was a great seminar, very informative, and
yeah, thanks for having me. It's been great.
Have a great summer, everyone. Talk to you later.
All right. See you, everyone.
Thank you very much.
Yeah, thank you so much. This is just fabulous. Great area to do research in.
Yeah, great. Appreciate it. Thanks for attending.
Excellent talk, even for a theoretical high energy physicist.
It's good to hear. Great.
Okay, very good.
Thanks.